All right, yeah.
Okay, so final presentation of this session on the connection between foundation models and our subfield, presented by Daniel.
Yes, thank you. Probably a very aggressive title here, so hopefully we can do it some sort of justice. All right, so I think one of the biggest promising application areas for our field is really in AI safety. If you don't care about AI safety, you might as well go and use a neural network, right? The interpretability that the symbolic components provide, as well as being able to formally sort of guarantee some of their properties, their behavior, super important for AI safety. So I think this is a big sort of area that we can move towards in the future. And a lot of us are dealing with these sort of tasks where we have perception, reasoning components. We're trying to find a way to plug them together to sort of get these benefits. But really the question we're asking in this paper is, should we be trying to train those components end to end from the perspective of moving towards AI safety? So some current approaches that are end to end, by the way, some of them engineer the reasoning component, your rules, you're giving them. Some of them are trying to even learn these rules, so it's an even harder problem. The claimed benefits of these end-to-end approaches is, well, firstly, you have this autonomy, right? This is in orange because I'm not so sure it's a benefit. We'll discuss that in a second. But the idea is you just give these like final labels at the end. You don't handhold the system. You just let it figure it out on its own. It's really autonomous. But we then end up with this somewhat interpretable system because we have these rules, even if you've engineered them. And the claim is that, well, that reduces the data labeling, right? We don't have to go and label concepts. We just give the final labels, and it saves a lot of engineering effort. But if anyone's tried to build one of these systems, I've tried a few times, it's really difficult to build a system that scales in this end-to-end setting, especially when you have a really complex bottleneck layer of concepts. Right, so the MNIST edition, it's nice, we all know and love that. I'll actually show some experiments on that as well, as everyone always does. But if you start to push that bottleneck to harder tasks where you have a much greater choice over what the concepts can be, it becomes really difficult to train these systems, even fully neural systems, actually. It's not just Neuro-Symbolic. It's obviously the Neuro-Symbolic is harder because we have these rules and we need to differentiate and backpropagate. It's even harder when you're trying to learn them, as I was saying. So we have this symbol grounding problem. And really, the sort of autonomy in terms of safety, I think some of you are probably familiar with this really great work from Mark Canato and their group on reasoning shortcuts. So the kind of setting here, I'll briefly explain. So if your knowledge base, whether you're learning the rules, whatever, here we're giving the rules. If there's a pedestrian or a red light, then you stop. In this situation, there's nothing to prevent the system from training the perception component as classifying pedestrians as red lights, right? You essentially have this disjunction, and there's no constraint that actually forces the system to behave in a way that we would just intuitively expect, right? So that when you come at inference time, maybe you have some new knowledge here, or maybe it's already existing in your knowledge base. You have if there's an emergency and there isn't a pedestrian, then you go. And in this case, because the perception models misclassified the pedestrian as a red light, you get the wrong answer. So this is a reasoning shortcut. It's where you have this, you have your rules and you're trying to then train the perception component. It's because you have this choice over the concepts and there's no signal to guide the perception model into learning the right concepts, even though you might get perfect accuracy in training on your downstream task. So if we're not training end-to-end, well, what else do we do? Well, it's kind of obvious, right? We have a pre-trained modular pipeline. This is nice because we don't have this reasoning shortcut problem, at least to the same degree. We also don't have this concept bottleneck problem where we're trying to backpropagate through this hugely complex concept layer, so we can scale more easily. But this requires data and engineering to configure. And also, there's kind of like a high skill bar to entry here where a machine learning engineer has to come in and design a specific CNN for your task, or if you're doing object detection, you need a YOLO model or something. And there's a lot of bespoke work that has to be done for the task. Unfortunately, it isn't the nice unified architecture that we all are trying to pursue. Unfortunately, I can't promise you that today either, but hopefully can convince you that maybe this is actually a better way to go from a practical perspective. So the question we're really addressing is, can we use the implicit knowledge that we have now in large foundation models to try and reduce the amount of data labeling engineering that we need on a pipeline, but whilst preserving those benefits that are really hard to obtain in end-to-end, right? So scaling and avoiding the reasoning shortcuts. So our method is pretty simple. It's a pipeline, as I said. So we're using something called BLIP, which is a vision language foundation model. So we don't have a CNN anymore. This is like an upgraded perception component. And you can use BLIP to do visual question answering. So you have an image of a playing card, you have a question, what rank is this? You pass it to BLIP and you get an answer, right? Natural language. So what we're doing is fine-tuning BLIP as our perception component with a few labels on what our concepts are. Now, there's a slight difference here than what we've done in the past. Because this is a foundation model, we don't need the concepts to be like really specific and atomic. You can have like a generic, or the label, sorry, that you're giving can actually be quite generic, a natural language description of what the playing card is. And then we're using a QA generator. You can engineer this if you want. You can use a language model. We'll show some results with that later. You take your space of labels, and then you generate a set of questions and answers to extract features from the image, right? So note here that we don't have any knowledge of what our downstream task is at this stage, right? We're just generating purely from the images a set of concepts using some implicit knowledge within our language model, if you're using a language model for this component, to generate the concepts. And our downstream task can figure out later what concepts we actually need. So then, if you're doing reasoning, you're done, right? This is, you can go home happy, you have your rules, you have your fine-tuned BLIP component, you're finished. We want to go a step further in sort of our line of work. We're always trying to learn the rules. And as I said, it became really difficult trying to integrate together in this end-to-end. But actually now rule learning becomes really easy, and we're able to use the rule learner to kind of explore the hypothesis space of rules, right? This is like an ILP problem, rather than trying to focus on working out what the concepts are. We want to use the rule learner for like what it's good at, right? It's already got a hard enough problem as it is trying to learn rules in sort of a large search space. So what we have is we take our images. Here, this is a simple card game. The rules are, the task is to learn the rules that define the winner, which is the player who's played the highest ranked card with the same suit as player 1 is the winner. So in this case, we assume ace is high, so player 4 is our winner. We take our questions that we have for BLIP, we extract features here, and then we have an example generator component. This can be manually engineered if you really want that control for safety applications. You can also use a language model to generate this, automate this, pass our extracted features to the symbolic learner, and then we learn our rules. Now here we can actually, the selection of the features can be in the example generator, because we give some knowledge about what the downstream task is at this point. It can also just go directly into the symbolic learner, and the symbolic learner can figure out what features to use to cover the downstream examples. So some results, everyone's favorite task. We have here reasoning. There's two tasks, sum, E9P. This is a slight extension because I forgot to mention we're working in ASP. I don't really care too much about what your logic, flavor of logic is you want to use. This framework is fairly general, but we're using ASP because we like to show with our lab what our lab does. We like to show expressivity and solving these combinatorial problems. And the E9P is just to demonstrate learning negation as failure. So the task it's a similar task to the sum, but if the first digit is even, you predict the value of the second digit. Otherwise, you predict 9 plus the value of the second digit. So it's kind of like same inputs, different label, different downstream task. And our graphs here show the accuracy of the downstream task against the total number of labels that we're using in our training. Now, these reasoning, we're giving the rules, so we have basically tried to select a variety of baselines that can learn ASP or learn or reason over ASP programs, but they're hopefully kind of reflective of a lot of the systems we find in the wider community. So we have Neuro-ASP, Embed to Sim. Janif is here as well. He's doing excellent work on Embed to Sim, so you can chat to him about that. Embed to Sim star is instead of learning a clustered embedding space from end-to-end training, we take an embedding space from a fine-tuned vision transformer, right? So it's kind of similar to our approach in that we're giving some concept annotations. Slash is a kind of optimization on Neuro-ASP to give some, it prunes the set of choices for your concepts based on how the gradient's accumulating during the early stages of training. And then blip plus ABL, we take blip, same fine-tuned perception, untrained, pre-trained but not fine-tuned perception component connected to an ASP implementation that we did of the abductive learning framework. So that's trying to identify pseudo-labels for fine-tuning that are kind of maximally confident while satisfying the downstream label. And what you can see is we essentially do pretty well here. Our graph slightly shifted to the left because in reasoning, obviously if we've fine-tuned a perception component, we don't need to train it, we're done. Neuro-ASP, embed to sim, slash, and blip and ABL, all end-to-end methods. So their total number of labels is at this sort of downstream end. And blip, by the way, is fine-tuned to a pretty good accuracy. We get 92% with only 100 labels. 97% with 1,000, which is within 2% of the state-of-the-art that has 60,000 labels. So the point is, like, yes, we're giving some concept annotations, but actually the number of labels you need to give is, when considering the whole end-to-end task, is actually less, because like with symbolic reasoning, you don't need any examples, right? You have the rules, but as you'll see now for learning, we only need a very few number of examples for symbolic learning to actually discover the rules. So in considering the number of labels end-to-end versus concept plus the task, it's actually a much smaller number that we have for doing a little bit of concept supervision. So our baselines here, FFNSL, this is one of our previous systems. It's basically the same kind of approach, although that's using a vision transformer, the best model from PyTorch that outputs like a softmax distribution. So it's not, I wouldn't call it a foundation model, because it doesn't have this large data set of vision and language. NSIL is also one of our systems that does end-to-end training, Neuro-Symbolic. VIT and reasoning net, so in this task, the reasoning net is an MLP. That's a fully neural baseline. We have blip and GPT-4, same fine-tuned perception component as us, and GPT-4 doing the reasoning, given the same inputs that you would to an ILP task. And then blip single image, we put all in this case, just the 2 digits in one image, give it to blip and ask it to predict the downstream label. And we actually fine-tune, train it in an end-to-end fashion. And again, you can see we have really good performance here, learning pretty high accuracy with a very low amount of data. Okay, so then this is the card game I mentioned. We have standard images. We have a more complex perception task here with card images from a Captain America deck. Again, we have really good performance here. The perception task is actually quite easy, slightly easier than MNIST. So blip gets really good accuracy. We can also learn the correct rules. But this is where the end-to-end methods really start to struggle, because we have 52 choices in the end-to-end setting for the first card, 51, 50, and 49, right? So if you multiply them together, you get about 6.5 million is the space of choices for your concept. Compare that to 100 with MNIST, 2-digit MNIST edition. So the end-to-end methods, you'll see some of them here, are starting to time out after 24 hours as we increase the number of data points that we have, whereas we're able to maintain good performance here. So this was pretty complex. We couldn't actually solve this task for a long time. When we were trying to learn the rules especially, it was very difficult. So we decided to push it even further to 10 players. So now we have a concept space of 5.74 times 10 to the 16, right, in terms of a full end-to-end setting. If you have the rules, it slightly prunes those spaces of concepts, but it's still pretty big. And again, because we have this separation now, we're not doing end-to-end training, our perception component is the same, right? It's completely unaffected by this change in the downstream task that's a lot more complex, that end-to-end methods then are hit by and really suffer. So you see the differences there. Because we're using a foundation model for perception, we can also do object detection, right? So this is where the visual question answering comes in pretty nice. because we can just train fine-tune Blip to extract, generate a caption for this image, which actually identifies what the objects are, their shape, their color, their size, etc. And we compare here to Alpha ILP, which is the state of the art on this task. It also does rule learning, so you're learning that they have these 3 classes, and it's like a kind of an arbitrary set of rules. It's like the first class, if there's a large cube and a large cylinder and things like this. So you see we've learned the correct rules, and we also get pretty good performance here with, again, a lot less data. So we're using 250 examples for our set of rules. We'd also run to their comparison with 500. They also do pre-training of their perception component. So they have 70,000 in their data set, but we actually, I think they had to use the original Clever images, whereas we just use the 9,000 from the Clever hands, so a significant reduction in the amount of data, and you can see that our accuracy is much better in those low label settings. So I'm probably running out of time, so I'm just going to quickly give you a flavor of the sort of prompts and the kind of second component or benefit of our work, which is trying to reduce the amount of engineering we're doing. So what I've shown you until now is reducing the amount of data labeling. So the prompts are actually much more verbose than this. I didn't put them all in the slides. But in terms of generating the questions and answers, this is using GPT-4. We just say you're required to generate a set of questions and answers. The task represents a handwritten digit. Downstream task description, perform arithmetic. So we're not giving any insight there into what the downstream task exactly is. We're just giving a general description of the domain and the space of concepts that we have. So what you see, wrap up? Yes, of course. So I'll summarize very quickly. So this is just showing the accuracy basically compared to fully manually engineered when we generate the questions and answers for fine-tuning automatically. MNIST struggles a little bit. You can ask me why later. This is then showing when we ask GPT-4 to generate the example generator component. So that's the glue that's taking the features from Blip and putting them into a symbolic learner. And the headline is, it works okay. It makes some mistakes. You can fix them very quickly using small manual tweaks. And you get some competitive results. And that's an extremely fuzzy conclusion there. But you can come and talk to me at the poster. So thank you.